Our next unit is a short, very, very short, one topic unit. Here's our goal. Here's a question that's going to be fair game. Figure that out without multiplying it all out. In other words, don't do this. This is not what we're going to call legal. For two reasons. One, it's going to take you a lot of time, be very inefficient. 4, 6, 7. And two, you're going to probably make at least one mistake, if not more, because the amount of calculations here is just off the chart. Nobody is going to do this by hand. So no, we are not going to do that. I claim I have a better way that will take you a lot less time. I would wager under 5 minutes. No joke. Under 5 minutes, maybe 6 minutes, depending how fast you write. There's another thing I could ask you. Without multiplying out this thing entirely, what number goes here in the answer? So in other words, when we are all done multiplying this thing all the way out without doing this, just give me the number of x to the sixths. I claim you can do that in under 60 seconds by the end of the unit. And you will be able to figure that out without having to know how many x to the eighths, how many x to the sevenths, and so on. Not by using magic, by using math and your brain. Probably a calculator. Okay. Before we get there, we have to do something else first. I'm going to create a structure. You may have seen this structure before. I'm going to start with the number 1. Below it, I'm going to put another 1 and another 1. Below that, I'm going to put a 1, a 2, and a 1. Underneath that, 1, 3, 3, 1. Beneath that, 1, 4, 6, 4, 1. Beneath that, there's another row that follows the same pattern. In fact, you could do this until you run out of room, run out of paper, run out of lead or ink. You can do this all the way to infinity if you like. If you know what the pattern is. And there is a pattern. It's very subtle and very simple. The key to this pattern is to notice, to get the next number, I look at the 2 directly above it. I know that's going to be a 1 because it's the sum of nothing and 1. There's a number that goes here. It's the sum of 1 and 4. There's a number that goes here. It's the sum of 4 and 6. The sum of 6 and 4. The sum of 4 and 1. The sum of 1 and nothing. And you can do that for all the rows above this as well. You can go back and check to see that, yes, this 4 is the sum of 3 and 1, and so on and so on. There's a name for this, and here's a much larger version of it, all the way down to the 11th row. This is called Pascal's triangle, named after a mathematician named Blaise Pascal. Pascal is known more in the fields of theology and philosophy, but he also did make a lot of important math contributions. He was one of the first people to develop probability theory. Probability really wasn't considered a mathematical subject until he wrote some papers on it and he analyzed different types of games and the mathematics behind them. Much of what we did in our last unit is owed to Pascal. There's also, those of you that are into computer programming, there's an old computer language called Pascal. Pascal is loosely based on the C language. If you've ever heard of C plus or C++, there's other variations of that. That all goes back to a programming language called Pascal. And Pascal created a very crude adding machine that could do very simple calculations that bookkeepers were able to use to do very simple calculations. It wasn't a widely used machine, but it was one of the first that could do very simple repetitive calculations. If you had to add up a whole bunch of sales, for example, in the 1600s, you could use Pascal's machine if you asked him to build you one. Well, this is Pascal's triangle, and it's got a lot of patterns in it. One pattern is that no matter what, this is all going to be ones, this is all going to be ones. This diagonal, and there's a mirror image on going down the other way, this diagonal are all the counting numbers, 1, 2, 3, 4, all the way on down. This diagonal has what are called triangular numbers. Numbers that if you use dots, you can write in little triangles. For example, 1, and then a row of 2 and a row of 1. A row of 3 dots, 2 dots, 1 dot. Bowling alley configuration, 4 dots, 3 dots, 2 dots, 1 dot. 5 dots, 4 dots, 3 dots, 2 dots, 1 dot, and so on. If you get a chance, Google triangular numbers, and you can look at that a little more in depth. And there are many other patterns in this as well. You could do a whole unit just on Pascal's triangle. Fortunately, we don't have the time to do that because some of the mathematics gets a little intense. Some notations here. This top one is called row 0. This is row 1. This is row 2. And so on and so on and so on. And a natural question is, why is the top one called row 0? Doesn't it make sense to call that row 1? Well, not really. And I'll show you why. This top one obviously is 1. This row, if we add up the numbers going across, adds up to 2. This row adds up to 4. This row adds up to 8. This row adds up to 16. And I think you can now see where this is going. 32. I'll give you a moment to find a pattern. This is 2 to the 0 power. We also called it row 0. This is 2 to the first power. We also called it row 1. 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. By the way, this is row 5. 2, 3, 4, 5. Row 5. That is not a coincidence. We can have a little more fun with Pascal's triangle. Find some other patterns here. Before I do that, I need to, well, I can do it this way. I can just insert that picture one more time. There we go. There's a fresh Pascal's triangle. I'm going to rewrite this row. This is 0, C, 0. How many ways, if I have nothing, how many ways can I choose nothing? One way. I claim this row is 1, C0 and 1, C1. If I have one object, how many ways can I choose nothing? One way. How many ways can I choose one object from a group of 1? One way. I'm going somewhere with this. Be patient. I have 2 objects. Number of ways I can choose nothing. I always have one way to choose nothing. I have 2 objects. How many ways can I choose one of those objects? 2. I can choose the object on the left or the object on the right. How many ways do I have to choose both objects? And again, we are assuming with C, order does not matter. I have one way to choose both objects. Three. This is row 3. By the way, remember, this is row 0, row 1. Look at all the left numbers. Row 2. Look at all the left numbers. Row 3. All the left numbers will be 3. There are 4 numbers in this row, so I can do 3C0, 3C1, 3C2, 3C3. 3 objects, choose none of them, one way. 3 objects, choose one of them, 3 ways. 3 objects, choose 2. Again, 3 ways. I can have AB. If my objects are A, B, and C, I can choose AB, AC, or BC. 3 objects, choose every single object, one way. Notice as the rows get longer and longer, we start to see patterns. 1, 5, 10, and then go backward, 10, 5, 1. 1, 8, 28, 56, 70, and then back down. Here we have a repeated number. In fact, every odd numbered row will have, oh shoot, there we go. Every odd numbered row, this is row 3, has a repeat. Row 4, no repeat. Row 5, repeat. This is 5C0, 5C1, 5C2, 5C3. If you remember our factorial notation, to calculate C, we had n factorial over r factorial n minus r factorial. So 5C3. N is 5. R is 3. This is 3. This is 5 minus 3 to give us 2. I wrote this wrong. This should be 5C2. There we go. Mistake corrected. It should be 5C2. So if I plug this one in, N is 5, R is now 2, I get 2 factorial times 5 minus 2, which is 3 factorial. 2 factorial, 3 factorial. Plugging in 5 and 3 gives me 3 factorial, 2 factorial. That's why we get a repeated value there. These two are the same. Because when we subtract them, we just get the reverse situation of the other one. Pascal's triangle can be thought of as a massive table of combinations. And this is one of the things that he really studied when he was working on probability. We're not going to use it for probability. We're going to use it to deal with this thing. How do you expand a binomial? If you recall from Algebra 2, a binomial is a quantity with 2 terms. And we're going to use Pascal's triangle to find a nice short way to multiply this out without having to multiply ourselves into a stupor here. We're going to use this as well to make it even shorter. So before we get to that, a couple of patterns I want you to notice. Back to Pascal's triangle. One more image here. And I don't need it as big for this one. This, I can think of as x plus 1 to the 0 power. Anything to the 0 power is 1. X plus 1 to the first. Anything to the first power is itself. I can also say that's 1x plus 1. Here's that one. I know that does not seem very impressive yet. Here's x plus 1 quantity squared. We know that to square a quantity, we square the first term. X plus 1 doubled, square the last term. We get the coefficients 1, 2, 1. X plus 1 cubed. If I multiply this out, trust me, you can multiply it out if you don't believe me. It's x cubed plus 3x squared plus 3x plus 1. 1, 3, 3, 1. 1, 3, 3, 1. 0 row, 0 power. First row, first power. Second, third, fourth, fifth, sixth, seventh, eighth. This is the 8th row. This is the 8th row. X plus 1 to the 8th is, go to the beginning, x to the 8th, 1x to the 8th, plus 8x to the 7th, plus 28x to the 6th, plus the next number is 56, x to the 5th, and so on until you get to plus 1. Our original problem was x plus 3, not x plus 1. Pascal's triangle is dumb. It doesn't work. It does if we adjust it. If we take this concept where we have the quantity x plus 1 to a power, and this concept where we have combinations and put them together, we will be able to do any polynomial. I'm sorry, any binomial to a power. One more example that I want to look at. I'll use x plus 2, and I will take it to the 0 power. I get 1, okay? X plus 2 to the first power is itself x plus 2. X plus 2 quantity squared is x squared plus 4x plus 4. But I claim Pascal's triangle is hiding in here. It's not hiding in the top run because that's obviously 1. It's hiding here. Our top row is 1, 1. I claim it's hiding here. This is really x plus 1 times 2. I'm going to rewrite that. 2 to the first. I claim Pascal's triangle is hiding in this one. I can rewrite this as 1x squared plus, okay, the row for this is 1, 2, 1. So I can take out a 2 here and get 2 to the first, x to the first, plus 1 times 2 to the first. Here's the 1, here's the 2, here's the 1. Pascal's triangle is hiding in this answer if we just rewrite it. Here's x plus 2 cubed. Pascal's triangle says it should be 1, 3, 3, 1. Well, this is really x cubed plus 6x squared plus 12x plus 8. However, if I factor out Pascal's triangle, I get x cubed plus, the next number should be 3. So I'll take it out. Take 3 out of 6x squared, and I get x squared times 2 to the first. Normally we would write that as 2x squared, but I'm using this to illustrate something. The next number is 3, divided out of 12x. That's 4x. Wait a minute. 4 is really 2 squared. 1 times 2 cubed, which is 8. 1, 3, 3, 1. And another thing I want you to notice, look at the powers of x as we go left to right. Cubed, squared, first, no powers of x. Look at the powers of 3. Nothing. I'm sorry, look at the powers of 2. Look at the powers of 2. Nothing, 1 power, 2 powers, 3 powers. As we go left to right, x drops a power every time, 2 gains a power every time. And look at the total number of powers in each term. 3 powers. 3 powers. X has 2 of them, 2 has 1 of them. 3 powers. X has 1 of them, now 2 has 2 of them. Here, 2 has all 3 powers. That is the secret to adjusting Pascal's triangle. when you don't have just x plus 1. Part 2, we're going to look at a slightly more complicated example, and then we're going to look at something called the binomial theorem, which is probably going to be the ugliest theorem you will encounter in your entire high school experience. Hopefully, I will make it simple to understand.